Today we're going to look at a linear quadratic regulation control, and it's also called a LQR. The problem that we have been dealing with from the previous chapters, those are all open loop control problems. The control is a function of time t. It's not a function of the state. Starting from this topic, we will present the closed loop optimal control of a linear planes with a quadratic performance index. Consider this system, x dot is equal to ax plus bu, and here a is a state matrix, and this is a function of time, and b is also a function of t. And x is a vector, u is a control vector, x is called a state, and yt is something we want to know from the system, that is a C matrix times the states. The C can be a function of a time t as well. The performance index is in the quadratic form. The first term over here, this is the terminal cost, and this form is called a quadratic form. You have a vector transpose times a symmetric matrix times the vector. And similarly, the other half of the performance index is in this integration form, and inside this integration you have two terms. One is about the state, the difference between z and y transpose times q times this vector, plus u transpose times r times ut dt. This problem depends on how we select z, tf, or whether we use the states or the observation. It can be further broken into two types of problems. One is called a regulation control, and the other one is called a tracking control. The regulation control means that you want to control the states or the output to 0. And the other one is called a tracking control. Tracking control means we want to keep the output all states along a desired trajectory. For the first case, you require zt is equal to 0. You will either drive yt goes to 0. If you pick x, you will drive x to 0. For today, we're going to look at the regulation problem. We want to control the states to 0 in a finite time. And let's look at these matrices that we used to define the performance index. We have the Q matrix. The Q matrix is called an arrow-weighted matrix. This is related to the states. And this matrix is a positive semi-definite. And the control-weighted matrix R is related to the control. It's used inside here. This matrix is a positive definite matrix. And the terminal cost of weighted matrix F is also positive semi-definite. We assume these three matrices are symmetric. If TF is infinity, and the terminal cost does not provide any realistic sense, if you don't know where the final time is, so in that case you will not have this term. And we're going to look at the first case, which is a finite time linear quadratic regulator. And in this problem we consider a linear time varying plant, which is that, with a cost function which is a half x transpose fx. We said it's a regulation problem. We wanted to drive the states to 0, plus the integration of x transpose times q times x, and as long as x is not 0, it will see some cost, plus the u transpose times r times u. So this is the cost function that we're going to use. And at the same time, we're going to make some assumptions. We assume that ut is unconstrained, and the tf is specified, because this is a finite linear quadratic regulation problem, and we'll specify a time. And xtf is not specified, or you can say xtf is free. And qt, ft are positive semi-definite, and rt is a positive definite. Given this assumption, and if you want to derive the optimal control for this problem in a closed loop form, and we can use the Hamiltonian formalism, or by follow the Pontryagin procedure, and let's have a quick review of that. If we use the Hamiltonian formalism or the Pontryagin procedure to solve the optimal control problem, and we'll define the Hamiltonian. The Hamiltonian is defined as a v function plus lambda transpose times everything on the right hand side of the dynamics equation. In this case, which is here, ax plus b times u. And we'll find optimum control by taking partial derivative of h over partial u, let that equal to 0. We'll be able to find an optimal control. And remember, this optimal control is just a relationship between the control and the co-states. Then we'll have the differential equations. There are two sets. One is the state equation, which is the same as the dynamics that we have. And the second equation is the co-state equation. Lambda dot is equal to negative partial h partial x. And on top of that, we have the boundary conditions in this form. And the boundary condition depends on the conditions that we give. And for this case, we are dealing with a problem that has a fixed final time. Delta TF will be 0 in this case. So you do not care about the coefficient for delta TF. And XTF is free. So it means that you will have the boundary condition as this is equal to 0. So the idea to derive the optimal control for this linear time varying system is to follow the Pontryagin procedure to obtain the optimum control, then propose the closed loop of configuration. So we know that these are steps that we're going through. Step 1, step 2, step 3, state a co-state equation, step 4, we're going to find a closed loop optimal control. And this is something new. And the first 3 steps are the same as what we did. And of course, we are dealing with a more complex scenario. We make it a general form, and x is a vector. You're going to see some derivations by using matrices and vectors. And last step, we're going to generate some new result, and this result will help us to solve optimal control problem. And this is called a matrix differential recursive equation. All right, let's see how we do that. So the first step, we're going to define a Hamiltonian, which will be half of this plus lambda transpose times f. Here, to simplify the writing, x here means the vector x, and it's a function of time t. And u is the same, is a vector u as a function of t. The b is a matrix b, and q is a matrix q as a function of a time t. R is a matrix of a function time t as well. Now the second step is to find optimal control. And optimal control requires partial h partial u is equal to 0. And here, u is a vector. And you probably don't remember how to take a partial derivative of this function with u. So before that, we'll have a review of how to take derivative of vectors and matrices. So here we're going to use a similar notation. X will be a vector, and A is a matrix. So the first partial A matrix times the vector X, partial X, this will give us the matrix A. And the second, the partial derivative of the multiplication of the two vectors, partial x transpose times y, and here there are all vectors. And if x is a vector, y is a vector, x transpose times y become a scalar. And we also know that x transpose times y is equal to y transpose times x. So this is the same as partial y transpose times x. If we take the time derivative of that, that will give us the vector x. The third one is x transpose times the matrix A times the vector y. This is equal to the same thing if we make a transpose of this whole thing. So if we make a transpose of this whole thing, that will become y transpose times A transpose times x. So it will become y transpose times A transpose times x. That will give us the vector of A transpose times x. You find a way that can help you to memorize this relationship. So you can see that if we're going to take a partial derivative of this term with y, and if you don't know how to do that, and you can probably do the transpose of this whole thing, because this is scalar. So this is equal to its transpose. If you do a transpose of vector multiplication, so it becomes y transpose put at the front, and this will be A transpose, then it will be x. X transpose, then do another transpose, it become x. So this is how we do it. and the two are the same, that give you this solution. Next is about this quadratic term. You have x transpose ax. So partial over partial x, and this is a quadratic term, x transpose times the matrix A times x. So now we have 2x. So you can use the chain rule. And at first you take a partial derivative with respect to this first x. That will give you ax. And if you take a partial derivative about the second x, that will give you a transpose times x. So that's why the solution is a times the vector x plus a transpose times x. And what happens if I take a second partial derivative of this? So we need to take another partial derivative of this with x, right? The first term that give us
A
is a, right? What is the second term?
A transpose.
A transpose. Exactly. So this is how we solve the problem. What if A is symmetric to A? That's why we keep mentioning that if we wanted them to be symmetric matrices, that can simplify the problem a lot. And we'll have a 2A there. That is partially why we want to keep this half. Because if we take a derivative and we'll twice, and we'll be able to see 2q, and it will cancel this half. Yeah. Come back to the optimal control. The optimal control, we're going to take a partial h, partial u is equal to 0. Now, I expect you to be able to do this. Let's do it together. So partial h, partial u, the first term is not about u. This term is about u. What do we have here? It's a symmetric matrix, and what do we have? It will be 2r times u, right? And 2r times u, and that 2 will be cancelled with that half. And remember, u, that is a vector. So, and how about here? And we need to take a derivative of lambda transpose times b times u with respect to u. What is that? So that will give us a b transpose times lambda. Lambda is a vector. That is equal to 0. This will give us optimal control. If we want to make it more accurate, we should put a star there, so that will tell us that this is the optimal control. The optimal control is related to optimal lambda. So what is the control? The optimal control will be equal to R inverse times the B transpose times lambda star.
Yes.
So this is the optimal control. It's a function of lambda. So the step 3, we're going to have the state and co-state equation, right? What is the state equation? The state equation is our dynamics. Of course, the state equation, we also need to write them at the optimum. So we probably use the same notation because I do not want to carry the t all over the places. We will be consistent with our own notation. A times x optimum plus bu optimum. And what is this? Let's see. So lambda star dot is equal to negative partial h, partial x, and h is here. Let me copy this over so that you can see clearly. So this is our h. So we'll do partial derivative of this with respect to x. So the first term, that will be, so let's put the negative sign there. It's at a qx, right? And it's after optimum. And the second term is not a function of x, which is nice. And how about this? It's A transpose times lambda. Great, we have these two equations. And we also applied the boundary condition to be able to solve them, right? So what are the boundary conditions for this problem? And we said this is for finite time, means TF is fixed. And XTF is free. TF is fixed. This is 0, and we do not need to care about this first term. And third XTF is random. This can be anything. So this is why we require this to be 0. And what is our S function? S function is from the terminal cost. We do have the terminal cost. Terminal cost is given here. This is our terminal cost. So the S function will be x transpose times f times x. And partial S, partial x, what do we have? This f times x. So this is at optimum. And f is evaluated at the time tf, right? So these are all evaluated at time tf, remember? TF times X star at TF minus lambda star at TF is equal to 0. So you can find a lambda TF. Lambda TF will be equal to F times X. Lambda TF is equal to F times X evaluated at TF. Let's look at the problem. We have the optimum control. Optimum control is this. And we wanted it to be a function of the states. And at the same time, we notice that this lambda at the time TF is a function, the X at TF. So it requires that at the terminal condition, it meets this requirement. And we were wondering, like, can we come up with a function that will make sure that toward the end this will be met and we share the same form, such that this u will be a function of x. So that comes to the closed loop optimal control. We assume we have a function, and this function lambda at any time t will be equal to matrix P times the optimal control. And we already know there must be one condition. P at a time tf need to be equal to f at a time tf, right? Otherwise this won't hold. So it requires P at a time tf is equal to f at a tf. And we just need to find out what this P matrix is. And this P matrix is a function of time t. So the next step is to find out what this P is. If we can solve the P, then you get an optimal control that will be a closed loop control, and you have a U that will be a function of lambda, and lambda is simply P times X. The problem is solved, so we are very close. So let's see how we solve this. So given that our optimal control U will replace lambda by this function Px. So this is our new control. And if we take the time derivative of this function, and what do we have? So that eventually we'll be able to find a relationship with the P only. So let's take the time derivative of that. So this will be lambda dot star, and we need to use the chain rule, right? Because P is a function of t, and X is also a function of t. So that will be P dot times X plus P times X dot. And we want to replace this lambda dot and X dot. Lambda dot is this, and X dot is that. Let's continue on this page because it's easier for us to see. So X dot is equal to that. So we're going to replace this. X dot is equal to that, and lambda dot is equal to this, and U is equal to this. So we're going to replace U by that. We have a minus sign, so we're going to put a minus sign here. And what else? This is lambda. Lambda is P times X. So replace this by P times X. Let's see what do we have. So let's put this out. This will be two terms. So we put a P there. So this will be P times that. And then we can move this out of the parentheses. That will give us that. And at the same time, look at it. They are all coefficient of X. So if we combine the whole thing together, it will be something times X is equal to 0, always. And since X is not always 0, and it requires the coefficient to be always 0. And the coefficient for X, we just simply need to just remove this. That will give us, all the rest will be the coefficient to X star. So it requires us to meet this requirement. We can move the left two terms to the right hand side. That will give us plus A transpose P, and at the same time move negative Q to the right hand side. That will be plus Q, and this negative Q will be gone, and this whole thing will be equal to 0. So now the problem becomes, what is this P? If we get the P, the problem will be solved. That is our original goal, right? So look at this. We have A that is known, A is known, Q is known, right? Q is given, and B is given, and R is given, and this is only a function about a P. So as long as we can solve this differential equation, then everything will be solved. And this magic expression has a cool name. It's called a matrix differential recursive equation. And we can also write this in the differential equation form. You can write it like this: P is equal to negative PA minus that minus Q plus PB R transpose B transpose times P. And remember, there's one initial condition which gives here. So let's bring this over here. And FTF is given. P is a function of time t, and the final condition is given. You do not know the initial condition, but you know the final condition. And you need to solve the problem backward. You know the final condition, then you do this integration, and you solve it backward so that you have a trajectory of this function p. And once you know this trajectory of function p, you will be able to get an optimum control. That optimum control is equal to a negative R inverse times B transpose times P times X. This is the whole process how we solve finite time linear quadratic regulation problem. Let's look at the property of this matrix P. And the first property of a P is symmetric. It's symmetric. You can find that by take a look at the solution to this. And if you put a P transpose, you replace P by P transpose, you satisfy this equation. And the final value of a P, TF, is equal to F at a time TF. So how do we know that it's going to minimize the performance index or maximize the performance index? And we need to verify the second order partial derivative of this Hamiltonian. Let's write it out. And the first term is a partial h, second derivative over partial x. And this is a partial h, partial x, and partial u. And this is a partial u square. And the diagonal entity here is the same. And what is the partial h, partial x square? So let's take a look at our h function. H function is over here. Let's take a second derivative of that with respect to x. It's just a q, right? So that is a qt. And how about a partial h partial u square, which is r? And what is the partial h partial x then partial u? If you take a partial derivative with respect to u first, that is not a function of x. This term is 0. Because q, r, and r, they are positive definite, so it implies this matrix is a positive definite. It implies that we are going to have a minimum.